In the autumn of 1912, at Lowell Observatory in Arizona, Vesto Slipher pointed a spectrograph toward the faint blur of the Andromeda Nebula and waited through the long patience that early astronomy demanded. The object was dim, stubborn, and difficult to capture. Nothing about the process promised revelation, yet when the spectral lines were finally measured, they carried a message that did not fit comfortably inside the universe. Most scientists thought they knew. Andromeda appeared to be moving, and moving fast. At first, that result did not open the cosmos. It only deepened the confusion if you place yourself for a moment in that world. The uncertainty feels almost physical. The great spiral nebulae were still mysterious. Some astronomers thought they were nearby objects drifting within the Milky Way. Others suspected they were vast systems of stars in their own right, scattered far beyond our galaxy. The scale of the universe itself was unsettled. The data were incomplete, the instruments demanding, and even the language of cosmology was still forming. A few strange measurements, however precise, were not enough to tell anyone what sort of reality they were standing inside. And yet the puzzle kept widening. Distances grew larger. Spectra grew stranger. Equations written to describe gravity began to suggest that the universe might not be fixed at all, but changing with time. Observers at telescopes, theorists at blackboards, and a handful of stubborn minds working across countries and disciplines were all circling the same possibility without fully grasping it at once. The discovery of the expanding universe was not a single flash of insight. It was something far more human, a slow assembling of clues, a contest between evidence and expectation, and a struggle to believe what the universe seemed to be saying. Tonight, we will step into that long moment of uncertainty, when the cosmos was beginning to outgrow old ideas, and no one yet knew what the final picture would be. How did a scattered set of observations become one of the deepest discoveries in the history of science? And what did it take for human beings to accept that the universe itself was not standing still? Begin with the sky as it first presents itself to a tired human mind. The dome of night lifts over a darkened landscape, and nothing in it seems hurried. The constellations hold their shapes. The familiar stars return to their appointed places. Even when the earth is turning beneath you and the hours are slipping by, the heavens can feel curiously resistant to change, as if they belong to a deeper tempo than weather, politics, memory, or the body. If you imagine yourself in an observatory a little after midnight, with the cold metal of the dome above you and the faint ticking of mechanical drives keeping pace with the stars, the impression grows stronger. The universe seems not merely vast, but settled. It seems composed. It seems like something that has already finished becoming what it is. That feeling matters, because long before astronomers discovered evidence that the universe is changing, they had to live inside a world in which stillness felt natural, almost self-evident. In the early 20th century, that intuition was not just poetic, it was close to a working expectation. According to the American Institute of Physics History of Cosmology, the common worldview held that the universe was static, more or less the same throughout eternity. That idea was not simply inherited from old religious pictures of the cosmos, or from the elegant geometries of earlier astronomy. It also survived because the sky itself encouraged it. Human beings had watched patterns repeat for so long that permanence felt less like a theory than like the backdrop of all theory. Stars were born and died on timescales no one had yet measured clearly. Galaxies had not even been recognized as galaxies. The as most people imagined it, was not a developing story. It was the stage on which stories happened, while the stage itself remained in place. Even among scientists, the notion of a large-scale cosmos that changed with time could seem not only difficult, but faintly improper,
The
as if one
velocity
were
of these
disturbing the
nebulae
dignity of the
suggests
heavens
a
by
scale
suggesting that
far
they had a
grander
history.
than previously
This is the
conceived.
mental atmosphere into which Einstein stepped after general relativity. His theory of gravity, completed in 1915, had already altered the meaning of space and time. Under its logic, gravity was no longer a hidden pull acting across emptiness. It was geometry itself, the curvature of space-time shaped by matter and energy. For the first time, the universe as a whole seemed to invite mathematical treatment. One could ask not only how planets moved, or how light bent near the sun, but what the overall architecture of the cosmos might be if Einstein's equations were taken seriously on the largest scale possible. That was a startling possibility. A set of equations first worked out in the context of gravitation near stars and planets now seemed capable of speaking about everything. The equations had quickly won prestige, and by the early 1920s, many leading scientists accepted that they could serve as a foundation for cosmology. Yet the moment those equations were turned toward the universe, they posed a problem. They did not naturally preserve the calm, motionless cosmos that intuition preferred. It is worth pausing inside that problem, because it was not merely technical. The old universe of common sense had no obvious reason to expand or contract. On human timescales, the sky gave no sign of swelling outward, and a collapsing cosmos seemed equally implausible. Einstein, like many of his contemporaries, wanted a universe that endured. But general relativity does not treat matter as passive decoration. Matter curves space, and curved space influences motion. Once the theory is applied to the universe at large, stillness becomes hard to arrange. Gravity gives the cosmos a kind of restlessness. If matter fills the universe, then on the largest scales, matter cannot simply sit there forever with no consequences. Space and time themselves respond. This was one of the quiet shocks of the new physics. A universe governed by general relativity was not a painted ceiling. It was a dynamical system. Even before anyone had observational proof of change, the mathematics had already begun to loosen the old image of an eternal cosmic still life. Einstein's answer in 1917 was ingenious, and in its own way deeply revealing. He published what later became known as the Einstein static universe, the first full relativistic cosmological model. In it, the universe was not infinite in the simple everyday sense, nor did it possess an outer edge one could imagine approaching. Instead, Einstein proposed a cosmos with positive spatial curvature, finite in volume but without boundary. It is one of the beautiful paradoxes of modern physics that a universe can be limited without ending, curved back on itself in such a way that there is no wall, no last frontier, no cosmic cliff. This was already a radical departure from older common sense. Yet Einstein introduced it in the service of preserving something familiar. He wanted the universe, once described, to remain globally unchanged. Motionless matter would fill this curved world, and the universe as a whole would endure in equilibrium. The strange geometry was new. The hope for permanence was old. To make that static world possible, Einstein added an extra term to his field equations, the cosmological constant. In later generations, this term would acquire an almost mythic status. But in 1917, its role was practical. Gravity alone would tend to pull matter together. The cosmological constant supplied a repulsive effect that could counterbalance that attraction on the largest scales. In the Einstein static universe, these influences were arranged in a delicate balance, producing a world that neither collapsed nor expanded. The model also assumed large-scale homogeneity. Matter, when viewed broadly enough, was taken to be spread more or less uniformly. Here was a universe of astonishing ambition, curved, finite, mathematically modern, and at rest. In one sense, Einstein had invented relativistic cosmology. In another, he had done so while trying to protect the ancient intuition that the universe should, in its deepest nature, simply be there. There is a psychological dimension to this that makes the story more human. Static worlds are easier to inhabit mentally. A changing universe implies a before and an after, perhaps even a beginning. And with those possibilities come questions about origin, fate, and instability. A static universe feels complete. It does not ask where it is going. It does not ask what it once was. It is not hard to see why many scientists found such a picture emotionally and philosophically congenial. The early 20th century was already an age of deep disruption. Classical physics had been shaken by relativity and quantum theory. European society had been scarred by war. Certainties were under pressure. In that setting, the desire for an ordered cosmic background was understandable. When the universe itself is imagined as changing, then change enters the deepest level of reality. The floor gives way. The heavens stop offering reassurance and begin to resemble history, full of development, contingency, and time. That was a very large step for the scientific imagination. And in 1917, most of the imagination had not yet taken it. What makes this moment especially striking is that the same mathematics that allowed Einstein to stabilize the universe also hinted that stability might not be the most natural reading. The AIP historical account preserves Einstein's reaction when Willem de Sitter produced equations that could describe a universe with expansion and a beginning. Einstein wrote that this circumstance irritated him. In another letter, he added that admitting such possibilities seemed senseless. Those are small phrases, but they open an intimate window onto the emotional texture of scientific thought. A discovery is often remembered as if a scientist simply follows logic wherever it leads. In practice, ideas arrive wrapped in taste, resistance, expectation, and the quiet force of what feels plausible. Einstein was not rejecting mathematics. He was reacting to what the mathematics appeared to be allowing reality to do. A universe that grows, or begins, or unfolds in time did not yet seem like an illumination. It seemed like an offense against coherence. And yet the 1917 model remains a foundational act. Modern mathematical cosmology begins there. As later historical studies note, Einstein had taken the equations of general relativity and applied them to the universe considered as a whole. That move was extraordinary. Every solution of the field equations could now be read as a possible universe. A new field of thought had opened, one in which space itself had global shape. Matter could be treated statistically on the largest scales, and the cosmos could be represented by competing models rather than merely contemplated as a philosophical given. At the same time, the Centennial Review of Einstein's 1917 paper points out some revealing limits. Einstein did not test the model seriously against astronomical observations. He did not analyze its stability in the way later researchers would. In other words, the first great relativistic universe was both brilliant and incomplete. It was not a final picture. It was a provisional shelter built at the edge of a new conceptual continent. If you stand for a moment inside that 1917 world, the story feels less like a chain of facts and more like a threshold. The old sensation of a still sky has not yet been broken. The observatories are watching, but they do not yet know what they are watching. The mathematics has widened reality, but it has not forced belief to follow. Somewhere in the tension between those two conditions, modern cosmology is being born, not in certainty, but in a new form of unease. The universe can no longer be treated as a harmless background. It has become a problem. A scientist can now write equations for the whole of it. Another scientist can object that the equations imply something intolerable. A third can begin to wonder whether the intolerance belongs not to the universe, but to the human mind confronting it. Long before expansion was established, the cosmos had already started to slip out of its ancient stillness inside thought itself. There was, however, a reason this first movement in the story could not remain purely theoretical. A dynamic or static universe is not something one decides by elegance alone. Mathematics may open the door, but observation has to decide what lies beyond it. And here the situation was even more unsettled than the equations. Astronomers did not yet know how large the universe was. They did not know whether the hazy spiral nebulae scattered across photographic plates were nearby structures inside the Milky Way or remote stellar systems far beyond it. Even the scale of the Milky Way itself was under revision. The ground beneath cosmology was still shifting. Before anyone could determine whether the universe was changing, they first had to determine what counted as the universe in the first place. That question would pull the story away from pure geometry and into observatories, photographic plates, distance estimates, and one of the most important scientific arguments of the early 20th century. So the stillness of the first section is only an apparent stillness. Beneath it, measurement is gathering force. Behind the calm face of the night sky, an argument about scale is beginning to sharpen. The next step in this journey will not ask yet whether the universe is expanding. It will ask something even more basic, and in some ways even more disorienting. When astronomers looked into the darkness beyond the stars, were they seeing the outskirts of their own galactic home, or the first hints of countless other worlds of stars, scattered through a cosmos far larger than anyone had comfortably imagined? From that question, the still universe would begin to crack. And so the question of motion had to wait a little longer, because another question stood in the doorway first. Before anyone could decide whether the universe was changing, they had to decide what exactly the universe included. If you place yourself beneath the observatory domes of the 1910s and early 1920s, the uncertainty does not feel abstract at all. Across the glass plates of the era were thousands of faint, cloudy objects, some diffuse, some elongated, some coiled into beautiful spirals that looked almost deliberate in their shape. They had been cataloged, photographed, argued over, and named, but not understood. Were these dim whorls, small structures, embedded somewhere inside the Milky Way, perhaps nearby formations of gas or stars? Or were they remote stellar systems, so distant that the whole of our galaxy was only one luminous province among many? That was no minor classification problem. It was the question that would determine the scale of everything that followed. At first glance, the older answer had a certain comfort. The Milky Way was already magnificent enough. It arched overhead as a dense band of unresolved light. And for many astronomers, it still seemed entirely plausible that this great stellar system was the universe in its practical entirety. The spiral nebulae were odd, yes, but odd things could still belong to one's own home. Their faintness did not prove distance. Their forms did not settle the matter. Even their place on the sky could be made to serve more than one interpretation. A galaxy-centered cosmos, especially after it had been enlarged by new work, still had intellectual gravity of its own. To imagine otherwise was to let the universe recede beyond intuitive grasp. It meant admitting that what looked like a pale smudge on a plate might itself contain stars beyond counting. That thought was available, but it had not yet become secure. The path toward a larger answer began, quietly enough, in a room of patient labor at Harvard College Observatory. There, Henrietta Swan Leavitt worked among the women computers who examined photographic plates by eye, comparing images of the same region of sky taken at different times and searching for minute changes in brightness. The work was painstaking, repetitive, and immensely demanding. A single plate held thousands of stars. To notice one variable star among them required more than diligence. It required the kind of attention that borders on a different mode of seeing, where tiny differences become legible because the observer has trained herself to live among them. Leavitt was assigned variable stars in the Magellanic Clouds, those irregular patches of light visible in the southern sky. And by following them carefully, she noticed something that did not at first announce itself as revolutionary. Certain variable stars, the Cepheids, seemed to obey a pattern. Those with longer periods were intrinsically brighter than those with shorter periods. That relationship sounds almost modest when spoken aloud. But in astronomy, it had the force of a key. Apparent brightness alone tells you very little, because a nearby dim star and a distant luminous one can look similar from Earth. But if a class of stars carries its own internal measure of true brightness, then distance becomes something you can infer rather than merely guess. Leavitt's Cepheids offered precisely that. Measure the period of the star's pulsation. Infer its intrinsic luminosity. Compare that to how bright it appears from Earth, and a distance can be calculated. For the first time, astronomers had a practical way of extending their reach far beyond the nearest stars. Leavitt herself did not live to see the full consequences of that discovery. And Harvard's own historical account is clear that the institutional limits placed on her role kept her from developing the broader theoretical uses of her work. Yet the ladder was there now, resting quietly against the dark. Others would climb it. One of the most important to do so was Harlow Shapley, working with globular clusters, those ancient swarms of stars that hang like remote lanterns around the Milky Way. He used Cepheid distances and other methods to map their distribution. What emerged from his work was deeply disorienting in its own right. The globular clusters did not seem centered around the sun. They were arranged in a pattern that implied a much larger galactic structure, with the sun lying far from the middle. In the American Institute of Physics Historical Reconstruction, Shapley's galaxy was 10 or even 100 times larger than previous estimates, and the solar system was many tens of thousands of light years from the galactic center. This was one of those moments when a technical adjustment in measurement alters the emotional architecture of reality. The Earth had already lost the center of the solar system. Now the sun itself lost the center of the galaxy, the universe, even before it multiplied into many galaxies, had already become more eccentric, less flattering to human instinct. Shapley understood that philosophical dimension and did not avoid it. The AIP history notes that he framed the change as part of a longer movement away from anthropocentric thinking. from a small universe with humanity at its privileged middle toward a larger and more indifferent order. His Milky Way was no longer a modest island of stars. It was an immense, all-comprehending structure that could plausibly contain the known nebulae as well. Once you accept such a galaxy, the island universe idea becomes harder to visualize, not easier. If our own stellar system is already enormous, then spiral nebulae of comparable scale must lie at unimaginable distances. Curtis could argue that this was still possible. Shapley could answer that possibility was not the same as plausibility. In 1920, to many astronomers, that mattered. This was the atmosphere surrounding what later came to be called the Great Debate. On the 26th of April, 1920, before the National Academy of Sciences, Shapley and Heber Curtis faced one another over what was formally the scale of the universe. The title itself is revealing. They were not yet debating expansion. They were debating the size and structure of the known cosmos. Shapley defended his enlarged Milky Way and argued that the spiral nebulae were probably part of it. Curtis argued that the spirals were separate stellar systems, independent island universes, and that the Milky Way, though large, was not the whole. In retrospect, the debate is often reduced to a simple verdict, as though one man won and the other lost. The real situation was subtler. Shapley was largely right about the size of the Milky Way and the sun's off-center position. Curtis was right about the external nature of the spirals, according to the AIP account. However, Shapley had the stronger position in 1920 because the evidence then in hand still leaned his way. Curtis's argument had its own elegance. He pointed to novae in spiral nebulae and suggested that if these objects behaved like novae in our own stellar environment, then the spirals could well be remote systems of stars. He was also more willing than Shapley to let the universe fracture into multiple large structures rather than one dominant galactic whole. There was a philosophical boldness in that view, though it did not yet rest on decisive proof. Shapley, by contrast, spoke from the strength of a newly enlarged Milky Way, supported by his globular cluster work. It is one of the quiet ironies of scientific history that each man carried a vital part of the future while still remaining partly bound to the present. The debate, therefore, did not end the question. It gave the question a clearer form. The scale problem had been brought into the open, but the sky had not yet answered it beyond dispute. For listeners today, it may seem surprising that so much could remain unsettled when telescopes had already advanced so far. Yet astronomy at this scale is rarely transformed by a single visual impression. The eye sees form, but form alone does not yield distance. A spiral pattern may be close and small, or vast and far away. Even brightness can mislead when intrinsic luminosity is unknown. What the debate truly revealed was that astronomy had reached the edge of descriptive seeing. It now needed a more exact distance ladder, one that could travel outward far enough to test the spirals themselves. Until that happened, the universe remained suspended between two imaginations. In one, the Milky Way was the great totality, and the spirals were local appendages. In the other, our galaxy was one member of a larger scattered population. The difference between those visions was almost too large for intuition to cross unaided. It had to be measured. That is where the narrative begins to narrow toward a handful of objects and a handful of people. Edwin Hubble had already sensed, even in his 1917 doctoral work, how little was securely known about nebulae. The catalogs were full of them, yet their nature remained obscure. After World War I, he joined Mount Wilson Observatory, where the 100-inch Hooker telescope offered an entirely new reach into faint luminous structures on the sky. This was not simply a matter of larger mirrors producing prettier images. It changed what could be attempted. Hubble photographed nebulae relentlessly, classified them, and began searching for variable stars within them. In an irregular nebula, now known as NGC 6822, he found such variables and wrote to Shapley about the discovery. The exchange is revealing. Shapley, for all their scientific tension, immediately recognized what a powerful instrument the 100-inch had become in bringing out desperately faint objects. Everyone could feel that the measurement frontier had shifted. What remained uncertain was how far that frontier would carry them. The decisive object, of course, was Andromeda. For generations, it had been one of the most famous spiral nebulae in the sky, visible even without a telescope as a dim, elongated patch. By the early 1920s, it had become more than a beautiful target. It was a test case for the size of the universe itself. On the night of the 5th to the 6th of October, 1923, Hubble exposed plate H, 335H, with the Hooker telescope at Mount Wilson. At first, he marked a particular point of light as a nova, crossing his notation from the previous night into the developing chain of evidence. Then the pattern of brightness changed in the way a Cepheid variable changes. He crossed out the N and wrote the now famous VAR beside the source. Carnegie's archive of the plate still preserves that moment in ink. A small annotation on glass became one of the great hinge points in the history of thought. Because once a Cepheid had been found in Andromeda, Leavitt's relation could do what arguments and impressions could not. Hubble could estimate the object's true brightness from its period and use that to calculate the distance. In February 1924, he wrote to Shapley reporting that the distance to M31 came out to something over 0 parsecs, roughly 1,000,000 light-years in the language of the time, and several times beyond Shapley's estimate for the outer limits of the Milky Way. The old ambiguity could no longer survive intact. If the distance was even roughly correct, Andromeda was not a local cloud, not an internal appendage, not a minor structure tucked within our galactic home. It was a separate galaxy. The island universes were no longer philosophical possibilities. One of them had been measured. Shapley's response has survived because it captured the human dimension of scientific correction with unusual grace. Reading Hubble's letter in his office, he remarked to a colleague, "Here is the letter that has destroyed my universe. It is one of the most quoted lines in the history of astronomy, and not because it is theatrical. It is memorable because it is so exact. A world picture had been built with care, supported by serious reasoning and real evidence, and now a new measurement had reached past it." Yet the remark was not merely bitter. The same historical record notes that Shapley accepted the reality of the variables once Hubble had enough photographic material, and he welcomed the definite solution to the nebula problem, even though it overturned earlier conclusions. That, too, belongs to the psychology of discovery. Sometimes the universe grows at the expense of one's own argument, and the real measure of scientific character lies in following it anyway. The formal announcement came on New Year's Day, 1925, at a meeting of the American Astronomical Society. And over the next few years, Hubble added further detail until the broader community accepted that the spiral nebulae lay outside our galaxy. The scale of the known cosmos widened again with startling force. Shapley had already displaced the Sun from the galactic center and enlarged the Milky Way by an order of magnitude. Hubble, using Leavitt's measure and Mount Wilson's reach, multiplied the inhabited astronomical universe yet again. From now on, the Milky Way would no longer stand as the all-comprehending unit of creation. It would become one galaxy among innumerable others, each a possible world of stars separated by distances so vast that even imagination had to proceed by discipline rather than instinct. And once that enlargement had been accepted, the strange spectral shifts that observers had been collecting no longer belonged to curious nearby clouds. They belonged to galaxies, which meant that the next question, waiting just beyond the edge of this one, would no longer concern scale alone. It would concern motion on the grandest scale anyone had ever dared to consider. Once Andromeda and the other spirals had been allowed to stand at extragalactic distances, the old photographic plates acquired a different kind of weight. Those faint smudges were no longer merely curiosities of form, no longer possible appendages inside a single galactic home. They were vast stellar systems, scattered through an enlarged universe. And that meant the strange displacements already seen in their light could no longer be treated as local oddities. They belonged to galaxies. The next question, then, did not arrive as a philosophical speculation or as an elegant equation written against a blackboard. It arrived as a practical astronomical problem. How fast were these remote systems moving? And what, if anything, had their light already been trying to tell us? To follow that question back to its beginning, you have to return to a very different moment, years before the scale of the universe had been settled. In 1909, at Lowell Observatory in Flagstaff, Percival Lowell asked his assistant Vesto Melvin Slipher to do something that did not sound impossible until one actually tried it. Lowell suspected that spiral nebulae might show spectral lines, just as stars and planetary nebulae did, and he wanted those lines photographed and measured. Slipher was not immediately confident that the task could be done. Spiral nebulae were faint, diffuse, extended patches of light. They were not bright points like stars. To photograph a stellar spectrum was difficult enough. To photograph the spectrum of a pale whirl suspended in darkness was something else entirely. The object did not yield itself all at once. It had to be coaxed onto the plate, almost persuaded to appear. What Slipher grasped, and this is one of the most consequential technical insights in the history of cosmology, was that the limitation did not lie exactly where many would have expected. For extended objects like nebulae, the decisive factor was not simply telescope aperture. A larger telescope certainly helped, but the real bottleneck was the speed of the spectrograph camera. The efficiency with which very faint, spread-out light could be recorded photographically. The rival observatories at Lick and Mount Wilson had larger instruments and skilled observers of their own. Slipher's advantage emerged from a different sensitivity. His willingness to rethink the optical problem itself. At Lowell, he improved the Brassier spectrograph with the help of machinists and instrument makers, replaced multiple prisms with a single high dispersion prism, used a wider slit, and most importantly, increased the speed of the camera dramatically. In one historical account by roughly a factor of 30. The discovery that followed would later look like a theoretical turning point, but it began as a triumph of instrument craft. There is something quietly beautiful in that fact. Before the universe could be seen differently, a camera had to be made faster. A lens had to gather light more efficiently. A plate had to endure exposure after exposure through long, cold nights. Discovery here was not the sudden appearance of cosmic truth in an isolated mind. It was hours of adjustment, stubbornness, patience, and the unglamorous intelligence that recognizes where an apparatus is truly failing. The expanding universe, in one of its first deep roots, depended on a man looking at a technical obstacle and realizing that the sky was not the only thing that needed interpreting. Then came Andromeda. On the night of the 17th of September, 1912, Slipher exposed the plate that would lead to the first measured Doppler shift of a spiral nebula. The first of those plates, as later conference proceedings and historical reconstructions note, involved an exposure of 6 hours and 50 minutes, and further exposures over subsequent nights were needed before the result could be trusted. In the fall and winter of 1912, he made 4 plates of the Andromeda spectrum. When the lines were measured, they were shifted toward the blue. Using the Doppler interpretation familiar from stellar spectroscopy, Slipher concluded that Andromeda was approaching the solar system at about 300 kilometers per second. Even now, that number carries a certain force. At the time, it was astonishing. An order of magnitude larger than the velocities commonly associated with stars and nebulae. Slipher himself briefly wondered whether such a value could really be a Doppler velocity at all, but he could find no better explanation. That first result is one of the most useful correctives to the simplified memory of the expanding universe. The earliest decisive clue was not a redshift, it was a blue shift. The most famous nearby large spiral on the sky did not seem to be rushing away into cosmic recession. It seemed to be coming toward us. If you imagine yourself as an astronomer in 1912, the universe has not yet become a grand coherent motion outward. It has become stranger in a less orderly way. One luminous spiral is moving at a speed so large it almost feels improper. And it is doing so in the wrong direction for any later neat story of universal expansion. History often looks cleaner after the fact than it did from inside the room. Slipher's first success did not open onto certainty. It widened the field of confusion. Others were impressed immediately. William Campbell of Lick Observatory wrote that the Andromeda velocity was surprising in the extreme, and the result did not remain a Lowell curiosity for long. Francis Pease at Mount Wilson, Joseph Moore at Lick, and Max Wolf at Heidelberg confirmed the measurement independently. Confirmation mattered, because numbers of that scale could easily have been dismissed as instrumental illusion. But the high velocity would not go away. It survived scrutiny. And with that, the spiral nebulae began to pull themselves loose from older expectations. Lowell and Slipher had initially approached them partly in the spirit of the nebular hypothesis, the old idea that such spirals might be solar systems in formation. Velocities of this magnitude did not sit comfortably inside that picture. Whatever these objects were, they were not behaving like quiet, local structures, slowly condensing into familiar planetary order. Slipher did what good observers do when one startling result appears. He continued. Over the next 2 years, he measured more spiral nebulae, and the pattern that emerged was far stranger than a single extreme approach speed. A few early objects suggested a directional drift, approaching spirals toward one side of the sky, receding ones toward the opposite side. Slipher proposed that perhaps our own galactic system was moving relative to the nebulae, toward the south and away from the north. That interpretation made a kind of provisional sense. It preserved a local kinematic explanation and did not require any sweeping reimagining of the universe. Yet as the sample grew, the pattern became harder to keep in that form. Receding spirals appeared on both sides of the sky. The apparent drift remained tempting, but the data were beginning to overgrow it. In March 1914, Slipher published a short note announcing the radial velocities of 3 spiral nebulae, along with others reaching roughly 1,000 kilometers per second. Among them were objects now familiar under names like M77 and the Sombrero Galaxy, though in those years they still belonged to the hazy class of spirals whose nature had not been finally settled. The response within the astronomical community was immediate enough that when Slipher presented fuller results at the American Astronomical Society meeting in Illinois in 1914, he reportedly received a standing ovation. Campbell called the work one of the greatest discoveries astronomers had encountered in recent times. Those reactions are worth lingering over. They show that the startling character of these measurements was visible well before anyone could fit them into a finished cosmological framework. Astronomers did not yet know what the nebular velocities meant, but they knew they were seeing something profoundly out of scale with ordinary celestial motion. By 1915, Slipher had added 11 more nebulae to the list, and by 1917, he had published radial velocities for 25 spiral nebulae. By the early 1920s, he had pushed the total farther still, eventually circulating tables of 41 such measurements. Most were redshifted. Most were receding. A few, like Andromeda, still approached. But the larger impression was unmistakable. Very large recession velocities greatly predominated. Arthur Eddington, cautious though he remained, would later write that there was no doubt large receding motions predominated among the nebulae measured chiefly by Slipher, even before their distances were securely known. The spectra were already teaching astronomers an uncomfortable lesson. The spiral nebulae were the most swiftly moving objects then known in the universe. That phrase, the most swiftly moving objects in the universe, was not retrospective embroidery. In 1921, discussing the faint spiral NGC 584 in the New York Times, Slipher described it in almost exactly those terms after measuring a recessional speed of about 100 miles per second, roughly 770 kilometers per second. The object was thousands of times fainter than Andromeda, and that faintness itself hinted at great remoteness. Yet somehow, from that nearly lost light, the lines had still been extracted and their displacement measured. The achievement was both observational and imaginative. To look at something barely visible and in for motion on that scale required trust. Trust in the instrument, in the photographic chemistry, in the comparison spectra, and in the Doppler method itself. The numbers were so large that for a while, they strained the credibility of the very techniques that produced them. Here, perhaps more clearly than anywhere else in the early history of expansion, you can feel how observation runs ahead of interpretation. The spectral lines were objective marks on a photographic plate. Their displacement could be measured, but the meaning of that displacement still floated among competing possibilities. Was it true motion through space? Was it some effect of our own system's drift relative to the spirals? Did it imply that the spirals themselves were special, perhaps youthful or somehow dynamically anomalous? Slipher, at one stage, even wondered whether radial velocity might correlate with a nebula's stage of development. It was a reasonable attempt to interpret pattern from too little context. The observations had opened a door, but beyond that door was not yet a clean cosmological narrative. It was a chamber full of echoes. The social setting of the work mattered too. Lowell Observatory did not enjoy the same prestige as some of its larger rivals, and historical accounts of the period note that Lowell sometimes struggled to gain full acceptance as a peer institution capable of producing reliable and convincing discoveries. That background gives Slipher's achievement an added texture. He was not simply collecting difficult measurements. He was producing them from an observatory that did not automatically receive the benefit of the doubt. In another scientific culture, such work might have been absorbed more quickly into consensus. Here, the path was slower. Recognition came. Certainly, but so did hesitation. A remarkable result from a somewhat embattled institution had to win its legitimacy one plate at a time. And still the deeper implication waited just beyond reach, because something indispensable was missing. Velocity by itself does not tell you whether you are seeing a random scatter of motions, a local kinematic arrangement, or a general law of the cosmos. For that, you need distances. De Sitter could look at the redshifts and wonder whether some relativistic effect on light might account for them. Slipher could look at the sky distribution and still try to preserve a drift hypothesis. Others could simply marvel at the magnitudes and postpone judgment. The nebular spectra had established one fact beyond dispute. These objects were moving in a way no astronomer had expected, but they had not yet said whether the universe itself was dynamic, nor had they eliminated more conservative readings. The clues were real. Their final arrangement was not. There is something almost poignant in that interval. A human being, working with improved optics in the high thin air of Arizona, had already extracted from faint smears of light the first empirical signs that the cosmos might be unlike anything the older static imagination had allowed. Yet even such evidence could not force immediate understanding. That is often how major discovery proceeds. The world speaks first in fragments. It offers up a pattern partially out of order and asks to be endured before it can be explained. Slipher's spirals were already whispering of a universe in motion, but they were whispering through ambiguity, through one famous blue shift, through many accumulating red shifts, through technical difficulty, through incomplete theory, through a set of numbers that looked almost too large to belong to reality. And because the evidence arrived in fragments, it also became vulnerable to detours. Large redshifts could be interpreted in more than one way. Apparent motions on the sky could suggest an entirely different cosmic arrangement. A few plausible wrong turns, joined to a general reluctance to let the universe itself become historical, were enough to slow the meaning of the spectra for years. So as we move forward from these plates and these improbable velocities, we do not yet enter clarity. We enter the next and perhaps most revealing phase of the story, the phase in which bad evidence, persuasive error, and genuine conceptual ambiguity kept the right conclusion from settling cleanly into place. By now, the clues ought to have been coming into focus. The spiral nebulae had begun to feel larger, stranger, less domestic than they once had. Slipher's spectra had shown motion so great that they no longer sat comfortably inside older pictures of the heavens. And yet the closer astronomers moved toward a general answer, the more the whole matter seemed to blur. This is one of the most important things to feel in the history of the expanding universe. The right evidence did not arrive in a world ready to receive it. It arrived in a field of half-certainties, technical limits, philosophical preferences, and strong observational habits. For a time, nearly every new fact seemed capable of serving more than one story. Slipher himself had not begun with the idea that the universe was opening outward in all directions. His first pattern seemed more local than cosmic. Some of the early spiral nebulae he measured appeared to be approaching from one side of the sky, while others on the opposite side were receding. That suggested a simpler interpretation, one rooted in motion through an already established stellar environment. Perhaps it was our own system, or our own galaxy, drifting relative to the spirals. The thought was not foolish. It was a reasonable attempt to preserve coherence when only a small number of measurements existed, even after further observations began to weaken that interpretation. Slipher did not at once abandon it. He had discovered something extraordinary, but the extraordinary thing did not yet have a clear shape. Then there was De Sitter. His 1917 cosmological model, unlike Einstein's matter-filled static universe, described an empty cosmos with a peculiar property. The farther away an object lay in the chosen coordinates, the more its light would appear shifted toward lower frequencies. In later language, one could call this a redshift, but at the time, its meaning was much less settled. Did the light change because the source was rushing away through space, as in an ordinary Doppler interpretation? Or did the shift arise from the structure of space-time itself, even in a universe that was, in some formal sense, still static? The distinction mattered enormously. It meant that a redshift need not immediately force the conclusion of literal large-scale recession. One could look at Slipher's spectra and still imagine that the cosmos itself had not started moving. That ambiguity gave the early 1920s their peculiar texture. The observational evidence was unsettling, but the theoretical alternatives had not narrowed enough to settle the matter. The same spectral displacements could be read in more than one conceptual key. De Sitter's model seemed especially tantalizing because it appeared to offer a way of keeping cosmic change at arm's length. Something was happening to the light. Certainly, yet perhaps that something did not imply an evolving universe after all. Historians later noted that the apparent static character of De Sitter's model was itself a mathematical and interpretive complication, bound up with coordinates and with the difficulty of deciding what was physically real in a new relativistic language. To astronomers trying to make sense of data in real time, though, the appeal was simpler. It let them postpone the most disturbing conclusion. The atmosphere around these debates was also shaped by war. When Einstein was developing his early cosmological ideas and corresponding with De Sitter, Europe was in the middle of World War I. Communication between German scientists and the English-speaking world had been badly disrupted. According to the AIP historical account, Einstein probably did not know the crucial spiral nebula observations when he was formulating his model, and De Sitter himself had only an incomplete second-hand report of them. That is more than an incidental detail. Scientific knowledge often appears, in retrospect, as though it moved along a single continuous thread. In practice, it can travel slowly, unevenly, across languages, institutions, and broken channels of contact. The expanding universe was not only hard to infer, it was hard to circulate. So the field entered the 1920s, carrying multiple kinds of incompleteness at once. Observers had velocities without secure distances. Theorists had cosmological models without any agreement on which features of those models corresponded to nature. Astronomers were still arguing over whether the spiral nebulae belonged to the Milky Way or lay far beyond it. And beneath all of this was a deeper reluctance, inherited from the previous section of our story, to let the universe become historical. A static cosmos still felt intellectually cleaner. It was more symmetrical, more final, less exposed to awkward questions about origin and change. Under those conditions, false trails were not mere accidents. They were almost invited. One of the most persuasive of those false trails came from Mount Wilson Observatory, and from an astronomer whose work seemed to offer exactly the kind of evidence everyone wanted. Adriaan van Manen did not deal in abstract geometry or disputed spectral interpretation. He worked with photographic plates. He compared images of spiral nebulae taken years apart and believed he could identify specific points within them, almost like stars, whose tiny shifts revealed internal rotation. This kind of claim had a powerful intuitive force. If one could see a spiral nebula turning on the sky over a humanly manageable span of years, then the object must be relatively nearby. A truly immense stellar system far beyond the Milky Way would be too distant for such motion to register so quickly. Here, at last, seemed to be direct visual evidence, the sort that bypassed speculation and spoke for itself. It is easy, from a later vantage, to say that Van Manen was wrong and move on. But his measurements deserve a slower look, because they show how error can become convincing when it fits the broader landscape of uncertainty. The spiral nebulae, after all, were already puzzling objects. They were absent from the plane of the Milky Way, which some took as a sign of physical connection to our galaxy, not evidence of obscuring dust. Studies of novae in the spirals had not yet resolved the scale problem decisively for everyone. Shapley's enlarged Milky Way made it easier, not harder, for many astronomers to imagine that the nebulae belonged inside a single giant system. Van Manen's claimed rotations slid neatly into that context. They did not create skepticism about island universes from nothing. They gave skepticism a quantitative, observational body, and the implications were severe. If the spiral nebulae truly were separate stellar systems at enormous distances, then the rates of rotation Van Manen thought he had measured would imply tangential speeds greater than the speed of light. That was impossible. The conclusion seemed unavoidable. Either the spirals were nearby objects, small enough for their apparent motions to be real, or some fundamental principle of physics had already failed. Faced with those alternatives, most astronomers did not leap toward the breakdown of relativity. They moved toward the more conservative reading. Van Manen's results therefore acted as one of the strongest observational objections to the very idea that spirals were galaxies in their own right. A mistaken measurement, in this case, did not merely add noise. It actively stabilized the older picture. There is a deeply human texture to that episode. The AIP history puts it with rare clarity. Van Manen, with honest intentions but mistakenly, had seen what he expected to see. That sentence belongs to a larger history than astronomy alone. Scientific instruments do not eliminate the observer. They refine the observer's encounter with ambiguity. When measurements lie near the edge of what a method can bear, interpretation seeps into perception. The photograph seems objective. The plate feels like a witness. Yet the witness still has to be read. Van Manen had taken precautions. He was not fabricating results. He was working inside the ordinary danger that hovers over precision science, where the mind begins to notice a pattern just before nature has truly supplied one. His position also carried institutional weight. Mount Wilson was not a fringe site speaking into the dark from nowhere. It was one of the leading observatories in the world, and Van Manen's work circulated within a prestigious environment. The very location that would later become inseparable from the evidence for extragalactic distances and cosmic recession also sheltered one of the most persuasive obstacles to those conclusions. This is another reason the history matters. Scientific truth is not delayed only by ignorance or dogma. It can be delayed by competent people at first-rate institutions producing results that look serious, careful, and entirely compatible with the best available expectations. When that happens, the eventual correction may require not a single decisive refutation, but a slow shift in the balance of what different kinds of evidence are allowed to mean. Meanwhile, the redshift problem remained suspended between interpretation and measurement. De Sitter knew by 1921 of Slipher's velocity measurements for 25 spiral nebulae, and only 3 were approaching. Even so, he hesitated to draw sweeping conclusions. The pattern was suggestive, yes, but the other half of the relation, the distances, was still missing. Without reliable distances, one could not ask whether redshift increased in any orderly way with remoteness. The observations were like a set of disconnected bells ringing through the dark. They told astronomers that something was happening across the sky, but not yet what kind of geometry or history could join the sounds together. It is important. 2. Not to imagine that astronomers were simply being stubborn. They were trying to decide between live possibilities. Einstein's static model had one sort of elegance, though it required the cosmological constant. De Sitter's empty model offered a curious redshift effect, without committing immediately to a universe full of moving galaxies. The island universe view had gained ground, but not all objections had been cleared away. Measurements of nebular motion pulled one way. Measurements of apparent internal rotation pulled another, and the scale of the universe itself was still under construction. Around these issues, a broader philosophical mood lingered. Perhaps cosmology should proceed cautiously, avoiding grand claims until observations became firmer. In a domain this vast, caution could look indistinguishable from delay. You can almost hear the intellectual room tone of the period if you listen closely enough. Meetings where equations were discussed with an air of provisional confidence. Observatory offices where new plates were examined under magnification, carrying the quiet hope that the sky would finally choose one interpretation over another. Letters moving slowly across countries, then across languages, carrying partial knowledge. A world in which the universe had become a legitimate scientific subject, but had not yet become a stable object of knowledge. It existed as a field of competing models and incomplete correspondences. The heavens were no longer innocent, but they were not yet clear. Some of the conceptual fog also came from relativity itself. The new cosmology had introduced a realm in which one and the same mathematical structure might appear differently under different coordinate choices, and where intuitive ideas like rest, motion, distance, and time no longer behaved with old simplicity on the largest scales. Later historians noted that the apparently static character of De Sitter's universe was, in part, bound up with how it was written mathematically and interpreted physically. That meant astronomers were not only trying to read observations, they were also learning a new language of reality, one subtle enough to let a model seem static in one form and dynamic in another. The expanding universe, when it finally emerged, would not defeat a single error. It would have to survive a whole climate of ambiguity. By the end of the decade, even De Sitter himself would admit that neither his own solution nor Einstein's static universe could describe the observed world. And Eddington would ask the beautifully simple question that opened the next phase. Why should there be only static solutions at all? But that turn belongs to the movement ahead. For now, we are still in the interval where the universe refuses to explain itself cleanly, where good observations can point in opposite directions, and where bad observations can possess an authority of their own. To move beyond that impasse, cosmology would need more than patience. It would need a new willingness to follow the equations away from stillness, and to consider that change, not permanence, might be the more natural condition of the cosmos. So the way forward did not come first from the sky becoming simpler. It came from a different kind of patience, the patience of following equations past the point where intuition still felt at home. The observers had accumulated enough clues to unsettle the old picture, but not enough to close the case. Redshifts existed, distances were still uneven, and misleading measurements had given the static imagination one more excuse to linger. Under those conditions, cosmology could not wait for perfect evidence before thinking more boldly. It had to ask, with unusual seriousness, whether Einstein's theory itself had been pointing toward a changing cosmos all along, and whether the real obstacle lay less in mathematics than in the human reluctance to let the universe have a history. Einstein's 1917 model had created modern cosmology by treating the universe as something that could be described as a whole. That was already a profound shift. But the model he preferred was balanced into stillness by the cosmological constant, and that preference shaped the mood of the field for years. A few theorists looked at the same general theory of relativity and began to wonder whether stillness was being protected too carefully, whether it had been inserted as an expectation rather than recovered as a necessity. By the early 1920s, the central issue in relativistic cosmology was no longer simply how to write down a universe mathematically. It was how to decide which mathematical universes deserved to count as physically real, and whether time itself had to enter the structure of the cosmos more deeply than Einstein wanted. One of the first to push that question to its natural conclusion was Alexander Friedmann. He was a Russian physicist and mathematician working in the difficult aftermath of war and revolution, in a scientific environment where access to the European literature had only recently resumed. Physics. Today's historical account emphasizes both the intellectual boldness of his achievement and the harshness of the conditions in which it was made. Friedmann did not approach Einstein's model as something to defend. He approached it as one possible solution among others. In 1922, he published a paper showing that if one writes the most general form of a homogeneous and isotropic universe allowed by general relativity, then one is not confined to static worlds. The geometry itself can evolve. The cosmic radius can be a function of time. Space may expand, contract, or pass through cycles of growth and collapse. That change of viewpoint was subtle in form and revolutionary in consequence. Friedmann did not merely tweak Einstein's universe. He dissolved the presumption that a cosmos satisfying the broad symmetries of relativity had to hold itself eternally in place. In his 1922 work, he laid out several non-static scenarios. And in 1924, he extended the picture further by considering universes of negative spatial curvature, including infinite ones. The result was not a single expanding universe in the later simplified sense, but a family of possible cosmic histories. Some solutions opened outward, some eventually reversed. Some implied a beginning from a state of vanishing size. Others admitted an infinite extent. The modern habit of thinking about cosmology as a landscape of models, each with its own geometry and time evolution, begins in large part here. Friedmann turned cosmology from the search for one acceptable still image into the study of possible cosmic lives. The response was cool at best, and revealing at worst. Einstein's initial reaction was to reject Friedmann's 1922 solution as mathematically suspect. In a brief note, he argued that Friedmann had made an error. Effectively, because Einstein believed the equations still implied constancy of density, and therefore a fixed cosmos. Friedmann answered with a detailed letter defending his derivation. After Einstein finally saw the clarification, and after Yuri Krutkov discussed the issue with him in Leiden, he published another short note acknowledging that Friedmann's mathematics was correct. Yet even then, the concession stopped short of genuine acceptance. Einstein still regarded the solution as lacking physical meaning, or at least he remained deeply unconvinced that the real universe could behave in such a way. The correction mattered, but the reluctance mattered just as much. A dynamic cosmos had been found in the equations, and the founder of the theory still did not want to live in it. That episode captures a larger truth about scientific change. A mathematical result can be impeccable and still fail to persuade if it arrives before the community has learned how to think with it. Friedman's papers were difficult, conceptually unfamiliar, and only loosely tethered to observation. The redshift evidence existed, but it had not yet been organized into a compelling law. Distances remained too insecure to give the theory an immediate astronomical anchor. Even Friedman's 1924 paper, which widened the range of possible cosmologies still further, drew little notice. Physics Today notes that his works were published amid severe hardship and relative isolation, with German journals themselves appealing for help in restoring scientific literature to Soviet colleagues after war and revolution. Friedman died young in 1925, only 37 years old. The man who had first shown clearly that general relativity allows evolving universes did not live to see those universes become central to modern thought. And then, from a very different direction, came Georges Lemaître. His life carried an unusual combination of disciplines and experiences that suited the problem almost perfectly. According to the University of Louvain's biographical sketch, he began in engineering, turned after World War I toward physics and mathematics, continued studying relativity during his seminary years, and was ordained a priest in 1923. Soon after, with financial support arranged through Cardinal Mercier, he went to Cambridge to work with Arthur Eddington, then to the United States, where he spent time at MIT and at the Harvard College Observatory with Harlow Shapley. By the time he returned to Louvain, he was both a specialist in general relativity and unusually well informed about the latest astronomical data. He had lived, in other words, on both sides of the divide that still troubled cosmology, the abstract side of field equations and the observational side of nebulae, spectra, and distances. That dual fluency mattered. Friedman had shown that non-static universes were mathematically possible. Lemaître went further by asking whether they might also explain what astronomers were already seeing. His 1927 paper announced its intention in the title itself: a homogeneous universe of constant mass and increasing radius, accounting for the radial velocity of extragalactic nebulae. The title is almost a synopsis of the intellectual leap. Space need not be static. Its scale may increase with time. And the recession-like behavior of the nebulae may not be an isolated observational curiosity at all, but the visible sign of that enlargement. Later historical commentary describes this as the kernel of Lemaître's contribution, the feature that distinguishes him from Friedman. He did not simply rediscover dynamic solutions. He connected the changing geometry of general relativity to the already known redshifts of the nebulae. What Lemaître actually did in that paper was delicate and, for its time, remarkably modern. He considered a universe of constant mass with a radius changing in time. And from that framework, he derived the relation that recession speed should grow in proportion to distance. He then used the observational material then available, velocity data ultimately rooted in Slipher's measurements, accessed through a table by Gustav Stromberg, together with distance estimates then circulating in the literature to estimate a value for the rate of expansion. The data were still rough, much rougher than the cleaner relation that would later become famous. But the conceptual act had already occurred. In 1927, before the canonical 1929 paper, Lemaître had proposed that the nebular redshifts were the natural observational expression of an expanding universe described by general relativity. The theory and the evidence had, at least in outline, been joined, and yet the paper did not immediately change the field. Part of the reason was practical. It appeared in the Annales de la Société Scientifique de Bruxelles, a Belgian journal that later historians describe as a relatively obscure vehicle for this kind of work. It was written in French. Lemaître was still early in his career. The mathematical analysis was demanding. The observations used to support the argument were preliminary enough that even sympathetic readers may have hesitated. Later, historical studies explicitly note that the paper attracted little attention for several years, and that its neglect cannot be explained by a single factor alone. Publication venue, language, conceptual difficulty, and the tentative state of the data all played a role. The universe had been given a dynamic interpretation, but it had not yet found the audience required to make that interpretation widely felt. There is also a quieter, more personal aspect to Lemaître's place in the story. The Louvain sketch describes him as modest, cheerful, optimistic, and intellectually flexible, someone who did not seek fame, yet remained quite aware of the originality of his own ideas. Those traits fit the historical record rather well. He was capable of holding together domains that many around him kept apart: priesthood and physics, geometry and observation, formal theory, and the practical problem of nebular redshifts. He also seems to have been more comfortable than Einstein with the idea that the cosmos might unfold in time rather than simply endure. Physics Today notes that when Einstein met Lemaître in 1927, he still regarded the notion of an expanding universe with deep distaste. Lemaître, by contrast, treated time-varying cosmology not as an offense against reason, but as a consequence one ought to follow where the equations and observations seem to lead. In that sense, Section 5 of this story is not only about mathematical invention, it is about a change in intellectual temperament. Friedman loosened the hold of the static universe by proving that Einstein's field equations allowed whole families of evolving worlds. Lemaître then gave those worlds an astronomical face. He showed how a growing radius of space might account for the nebular redshifts that had accumulated in such puzzling fashion. Between them, the blackboard had ceased to defend stillness. It had begun to imagine history on a cosmic scale. But imagination, even mathematical imagination, could carry the field only so far. The dynamic universe was now a serious theoretical possibility, perhaps even the most compelling one. What it still needed was a firmer observational architecture, a distance scale solid enough, and a body of measurements broad enough to let the sky itself reveal that the pattern was real. That work would fall once again to telescopes, photographic plates, and the slow discipline of measuring the abyss. On some nights at Mount Wilson, the work began long before anything could be called a discovery. The dome would already be cold by the time the telescope was set in motion, its metal frame turning with patient heaviness toward a target too faint to impress anyone standing under the open sky below. Inside, the night was not romantic in the simple way later memory sometimes makes it seem. It was technical, deliberate, and physically demanding. Gears had to behave. The seeing had to hold. The guiding had to remain steady. And the observer had to stay alert through long stretches in which almost nothing visible appeared to happen at all. This was the kind of astronomy that asked the body to serve the mind. A distant galaxy did not reveal itself in one clean instant. Its light arrived weakened by distance, then weakened again by the spectrograph, until what finally reached the photographic plate was little more than a fragile trace. To stay with that trace for hours demanded a discipline that was almost monastic. The Earth kept turning. The instrument had to follow. A small failure of attention could ruin what the whole night had been trying to gather. Yet it was under these conditions, in this slow struggle with reluctant light, that the expanding universe moved from suggestion toward measurement. Mount Wilson had already changed astronomy once. The 100-inch Hooker telescope had helped push Andromeda and the other spirals beyond the limits of the Milky Way, turning them from uncertain nebulae into galaxies. That earlier triumph, however, did not settle the deeper question. It only sharpened it. Once these objects stood at truly immense distances, their motions became harder to treat as local irregularities. Slipher's redshifts no longer belonged to nearby curiosities of uncertain nature. They belonged to whole stellar systems scattered through intergalactic space. The sky had grown, and in growing, it had made velocity far more consequential. Still, distance remained the delicate part of the whole architecture. Cepheid variables had opened the first secure path outward, but only for galaxies close enough that such stars could still be found and measured. Beyond that range, astronomy had to proceed by extension and analogy. The brightest resolved stars in a galaxy could serve as indicators. So could apparent diameters, integrated brightness, and comparisons among systems thought to be broadly similar. None of these methods possessed the satisfying firmness of direct geometric measurement. Each carried uncertainty, yet the universe did not offer itself in neat concentric rings of accessibility. If astronomers wanted to know whether there was an orderly connection between remoteness and recession, they had to build a ladder long enough to test the question, even if some of its upper rungs were less secure than they would have liked. Edwin Hubble was unusually well suited to that sort of task. He had a taste for ordering things, for drawing structure from visual confusion, for treating the sky as something that might yield patterns if approached with enough discipline. He did not merely observe galaxies. He classified them, compared them, placed them within a morphological sequence, and looked for ways that one measurable property might lead to another. That habit of mind mattered here. A relation between distance and velocity could only emerge if someone was willing to treat galaxies not as isolated marvels, but as members of a wider population whose behavior might become intelligible when assembled carefully enough. Even that kind of intelligence, though, needed another kind of partner. The most punishing part of the work was observational, and it increasingly depended on a man whose route into astronomy had been anything but conventional. Milton Humason had not entered the field through the usual academic door. He had little formal education beyond childhood, and his early life on Mount Wilson had been practical rather than scholarly. He knew the mountain first as a place, then as a workplace, and only gradually as one of the centers of modern cosmology. Over time, through reliability, steadiness, and extraordinary skill at the telescope, he became indispensable. He was exactly the sort of observer that a history built only around famous names tends to hide in the margins until one looks closely at what the measurements actually required. Then he moves immediately toward the center, under the dome. That meant hours of guiding on targets that scarcely looked like targets at all. A galaxy that would later appear in a paper as a recession velocity might, in the moment of observation, present itself only as a pale blur, barely more substantial than the darkness around it. The exposures were long, sometimes extending across multiple nights. The telescope had to remain steady. The star image had to stay properly placed. The spectrograph had to do its work at the very edge of feasibility. And the plate had to survive development with the faint spectral lines still legible enough to be measured. The final result, when it appeared in print, could be reduced to a number, but before it became a number, it was an ordeal of attention. That is what gives this stage of the story its peculiar dignity. The expanding universe was not confirmed by a single dramatic glance through an eyepiece. It emerged through repetition, endurance, calibration, and the willingness to trust procedures that worked so close to failure that each success felt provisional until another success followed it. The great cosmic relation that later generations would learn as a law began, in practice, as a series of faint marks on glass produced under conditions that left ample room for fatigue, doubt, and error. The power of the result lies partly in the fact that it survived all of that. As the 1920s moved forward, Hubble and Humason were able to bring more galaxies into the record. Some of the velocity measurements still depended on Slipher's earlier work, which remained absolutely foundational. He had opened the spectroscopic frontier, and no later account can honestly begin the redshift story without him. But Mount Wilson now had the optical power, the institutional support, and the observational stamina to extend the sample farther than before. Galaxies that had once been too faint for practical measurement could now be drawn into the emerging picture. With each additional system, the underlying question became easier to ask in a disciplined way. Were the more distant galaxies tending, on the whole, to show larger redshifts? That question sounds almost simple when put directly. In practice, it had to be asked through layers of approximation. Distances were still uncertain. Some came from Cepheids, others from derived methods that depended on assumptions about luminosity and scale. The radial velocities, though more concrete in one sense, were not always easy to extract from faint spectra. There was still local scatter to contend with, since nearby systems could possess motions of their own superimposed upon any larger trend. And the conceptual language was still not entirely settled. Was one describing recession through space, or a broader effect tied to the structure of space-time itself? Could redshift and distance together reveal a genuine cosmic pattern? Or would the whole arrangement dissolve once the sample grew and the errors became clearer? For a time, the answer arrived gradually rather than all at once. The nearby galaxies did not line up into any perfect arrangement, which was not surprising. Objects close enough to be influenced by local gravitational relations could move toward or away from us in ways that did not reflect the broader order of the cosmos. Andromeda itself, the old troublemaker in this story, still approached. But as the measurements reached farther outward, larger recession velocities became more common. A rough tendency began to appear through the imperfections. The remoter the galaxy, the greater the shift in its spectral lines tended to be. The beauty of that emerging tendency was that it did not depend on a single instrument or a single intellectual style. It came from the joining of different kinds of labor. Leavitt's Cepheids had laid the groundwork for distance measurement. Shapley had helped alter the scale of the Milky Way. Hubble's work had established the external status of the galaxies and pushed outward on the distance ladder. Slipher had supplied the pioneering redshifts. Humason had helped extend the spectroscopy to fainter systems. Even the theories of Friedman and Lemaître, though not yet fully absorbed into the collective memory of the field, had prepared a conceptual world in which such a relation could mean something profound. By the time the pattern began to show itself, the expanding universe already belonged to many hands. In 1929, Hubble gathered the observational strands into the paper that would become the most famous single document in this history. A relation between distance and radial velocity among extragalactic nebulae. The title was characteristically restrained. It did not announce the final overthrow of the static cosmos. It did not proclaim a revolution in the nature of reality. It described, with almost severe simplicity, a relation. Inside that modest phrasing was a transformation, using distances for a set of galaxies and combining them with radial velocities. Hubble showed that the data exhibited an approximate linear trend. The farther away a galaxy lay, the faster it seemed to be receding. That linearity was the decisive emotional shift. Astronomers had long known that celestial objects could move. Motion itself was not new. But a regular connection between distance and recession suggested something larger than a collection of individual trajectories. It implied that the observed order of the galaxies might be expressing a general condition of the universe. The cosmos no longer looked like a fixed arena populated by objects wandering through it at random speeds. It began to look like a system whose large-scale structure and large-scale motion were linked. Even here, though, reality did not present itself with perfect neatness. Hubble's sample was small. The data were sparse by later standards. The distances, especially for the remoter galaxies, depended on a calibration that would later prove too short. The resulting expansion rate was therefore far too high, implying a universe much younger than later cosmology would accept. That problem would cast a long shadow. It meant that the great relation had been found in form while still being wrong in scale. Such moments are among the most revealing in science. They show that truth sometimes arrives in outline first, with the internal proportions corrected only later. The expanding universe was becoming visible, but it had not yet become numerically comfortable. That incompleteness mattered intellectually as well. A less careful retelling might suggest that once Hubble's 1929 paper appeared, doubt simply evaporated. The real atmosphere was more measured. The relation was striking, persuasive, and increasingly difficult to dismiss. But questions remained about interpretation and about the exact meaning of the redshifts. Hubble himself was more cautious than later public memory often allows. He was presenting an observational correlation, not writing a manifesto. There is something fitting in that restraint. The measurements had been won so painstakingly that they encouraged a kind of sobriety. If the universe was expanding, it was a conclusion to be approached with disciplined care, not with rhetorical flourish. Still, the psychological world of cosmology had changed. Once distances and velocities could be placed beside one another in this way, the static universe lost much of its shelter. One could still argue over interpretation, still raise doubts about calibration, still hesitate over theoretical language. But the deeper order of the data had begun to speak with unusual firmness. Redshifts were no longer isolated curiosities. Distances were no longer separate technical exercises. They now belonged to the same observational field. The galaxies, taken collectively, seemed to be participating in a larger recession pattern that no older, purely static picture could easily absorb. You can feel, at this point in the story, the different tempos of discovery beginning to converge. The slow tempo of observation, with its patient exposures and cautious measurements. The somewhat faster tempo of statistical recognition, when enough points on a graph begin to suggest a law. And beneath both of these, the long philosophical tempo in which human beings adjust to the idea that the universe itself may have a history. By 1929, those tempos had not merged completely, but they were closer than ever before. The mountain observatory, the photographic plate, the distance ladder, the redshift tables, and the non-static solutions of relativity were all beginning to speak to one another. There is also a certain irony here. The relation that would later become one of the most iconic results in modern cosmology emerged through methods that were, in many respects, still provisional. The galaxies were real. The redshifts were real. The statistical tendency was real, but the distances were not yet secure enough to make the universe numerically stable in human thought. In a sense, astronomers had reached the point where they could see the motion of the cosmos before they could fully trust the ruler with which they measured it. The abyss had been measured. Yes, but only by instruments and methods still learning their own reach. And that is precisely why the next part of the story cannot be told as a mere victory lap. Because once the observational relation was visible, another difficulty moved quietly into view. Who, exactly, had discovered it? Was this Hubble's relation because he had published the 1929 paper that fixed the pattern in the astronomical imagination? How much of its foundation belonged to Slipher, whose velocities formed the indispensable base? What place should be given to Lemaître, who had already connected redshifts and an expanding relativistic universe in 1927? And what happens, more generally, when a collective discovery passes through the narrowing filter of names, prestige, translation, and memory? The galaxies had begun to align into a cosmic pattern. Human history, as it turned out, was less inclined to line up so cleanly. And so the pattern, once it had finally begun to show itself, brought with it a second kind of difficulty. The galaxies could be arranged on a graph. Their distances and redshifts could be compared. A large cosmic tendency had emerged from years of work at the telescope and on the plate. Yet, almost as soon as that happened, the history of the discovery started to narrow around a smaller and more human question. When a truth arrives through many hands, through scattered papers, hesitant interpretations, forgotten journals, and institutions that do not all carry the same prestige, who gets remembered as the discoverer? The universe had become easier to picture than the path by which people had come to know it. Hubble's 1929 paper unquestionably matters. It gave the astronomical community a clear observational relation between distance and radial velocity among extragalactic nebulae, and it did so in a form that was portable, memorable, and hard to ignore. The paper was published in PNAS. The title was austere, and the result sat inside it with the force of plain evidence. The more distant the galaxy, the larger the measured recession tended to be. It is easy to understand why that paper became the fixed landmark in public memory. It took a difficult and scattered body of work and placed it into one short document that later readers could point to without having to relive the entire disorder of the 1910s and 1920s. But the closer one looks, the less the story behaves like a single discovery by a single person. Hubble's famous graph depended on distances that he and others had worked hard to assemble. Yet the radial velocities on which the relation rested came largely from Slipher's earlier spectroscopy. Long before the 1929 paper, Slipher had already built up the essential archive of nebular redshifts that made any velocity-distance comparison possible. Even later, historical treatments that remain respectful of Hubble's role are clear on this point. The observational foundation of the relation did not begin in 1929. By then, Some of the most difficult light had already been captured years earlier in Arizona. Then there is Lemaître. In 1927, 2 years before Hubble's paper, he published a study in which he did something historically decisive. He combined a relativistic expanding universe solution with the available observational data and obtained a linear relation between recession and distance. The later 2018 historical review in Galaxies states the point plainly. Lemaître announced the relation before Hubble, interpreted it through an expanding universe model, tested it against the available data, and was the first to connect the velocity and distance data to an expanding cosmology. That does not erase Hubble's achievement. It changes the nature of it. Hubble's paper becomes less the birth of the idea than the moment of its stronger observational establishment. This is where the story becomes especially delicate, because different historians place the emphasis in slightly different places. Some argue that Hubble deserves primary credit for the empirical demonstration that convinced the astronomical community. Others place Lemaître at the center, because he not only found the relation earlier, but also understood what it meant in the language of general relativity. Still others widen the frame and insist that Schleifer, and even figures such as Karl Wirtz and Knut Lundmark, must be restored to view if the story is to remain historically honest. One modern review goes so far as to say that if only 2 names are singled out for the general acceptance of cosmic expansion, the evidence points to Lemaître and Hubble, while also noting that Wirtz, Lundmark, De Sitter, and Schleifer all made indispensable contributions. Lundmark is a revealing case because he lives exactly in the zone between recognition and obscurity. Historical analyses note that in 1924, he published the first distance velocity diagram for spiral nebulae, with distances expressed relative to Andromeda, Wirtz, working around the same period. Also found suggestive relationships between apparent properties of spirals and their radial velocities. These were early, imperfect, and still entangled with unresolved assumptions about the scale of the universe. They did not command later memory the way Hubble's 1929 relation did. Yet they show that the basic shape of the problem had already been seen from more than one angle before the canonical paper appeared. The expanding universe was not hiding behind a single locked door. Several people had felt the handle. If the history had simply remained a matter of who published first, it would already be complicated enough. But there was another layer, and it concerned visibility. Lemaître's 1927 paper appeared in French in a Belgian journal that did not command the same international attention as the journals circulating most strongly through the English-speaking astronomical world. The paper existed. The argument was there. And yet the field did not reorganize itself around it. In science, a result can be present without being fully present. It can live in the literature and still fail to shape collective memory until someone with the right institutional position, language, or platform makes the same terrain legible again. That is one reason the 1931 translation episode has drawn so much interest from historians. Lemaître's 1927 paper was translated into English and published in monthly notices in 1931, which should have widened its reach considerably. Yet key paragraphs dealing with the numerical discussion of the radial velocities and the coefficient of expansion were missing in the English version. For many years, that omission fed suspicion and speculation. In 2011, however, a newly examined letter clarified that the cuts were made by Lemaître himself, who told the translator's intermediary that the provisional discussion of radial velocities was of no actual interest, very likely meaning no current interest, because more recent observational work had already appeared by then. The omission did not create Lemaître's neglect by itself, but it certainly helped later readers encounter a softened version of his priority. There is something quietly moving in that detail. Lemaître seems not to have been guarding priority with the vigilance later generations often expect from scientific actors in famous disputes. The letter, and the historical discussion around it, suggest a man more interested in keeping the science current than in preserving a monument to his own precedents. That does not make the historical distortion less real. It makes it more human. Credit is not always lost through theft in any theatrical sense. Sometimes it fades through translation, publication choices, modesty, timing, and the uneven ways communities decide what counts as already known. The Hubble side of the story is equally nuanced. Hubble was never merely a name attached by accident to other people's work. He helped establish the extragalactic nature of the spiral nebulae. He developed the distance ladder for galaxies with greater reach and authority than anyone before him. He and Humason strengthened the empirical case with additional observations from Mount Wilson. Yet historians have also pointed out that there is no clear evidence Hubble was searching in 1929, specifically for an expanding universe relation in the fully theoretical sense that later cosmology would attach to his name. One historical study puts it quite directly. Hubble may credibly be said to have discovered the empirical relation, but historians have not found evidence that he set out to uncover the expansion of the universe as such when he published the 1929 paper. That distinction matters because it opens onto Hubble's own caution, which was greater than popular memory usually allows. In later lectures published as The Observational Approach to Cosmology, Hubble wrote that if redshifts were genuine velocity shifts, then the observation suggested an expanding universe that was finite, small, and young. But he also insisted on an alternative possibility, that the redshifts might point to some unknown principle of nature rather than actual motion. The same work repeatedly presents a choice between those pictures instead of treating expansion as an unqualified and final verdict. A modern historical review summarizes this well by noting that Hubble was far from sure that redshifts should simply be interpreted as Doppler velocities, which is why he continued to speak carefully of apparent velocity. That caution can be read in several ways. One reading treats it as scientific prudence in the face of still imperfect data and an uncomfortable cosmic age problem. Another sees in it a deeper resistance to the more radical relativistic picture, especially the idea that space itself expands. Historians of cosmology have often noted that Hubble never fully embraced that interpretation. Even as his observation strengthened the case others would use to defend it. In that sense, the public phrase, Hubble discovered, the expanding universe is both true and not quite true. His work was central to the observational case. Yet the full conceptual meaning of expansion was articulated earlier by Lemaître, and Hubble himself remained more reserved about that meaning than the later textbook phrase suggests. Humason, too, tends to disappear from popular retellings at exactly the point where the observational burden becomes heaviest. That is one reason some historians prefer to speak of Hubble and Humason together when discussing the detailed observational confirmation of the relation. One recent review, quoting Mario Livio's summary of the historical record, argues that it is fair to credit Lemaître with the discovery of the expanding universe and the tentative existence of a Hubble law, while crediting Hubble and Humason with the detailed confirmation of that law. The phrasing is useful because it does not flatten the story into a single winner. It lets the discovery remain what it really was: layered, collective, and unevenly remembered. By the early 1930s, The astronomical community was moving toward acceptance of expansion, but the history of how it got there was already being simplified. Hubble's 1929 paper was easier to teach than the scattered earlier efforts of Wurtz and Lundmark. It was easier to cite than Slipher's years of spectroscopic groundwork. It was published in a prominent venue, in English, under the name of an astronomer who had already become famous for proving that spiral nebulae were galaxies. Scientific memory often favors the point where many strands become legible in one place. That preference is understandable. It is also one of the reasons later generations so often inherit discovery stories that are cleaner than the science itself ever was. The later attempt to correct that memory became public in an institutional way in 2018. When the International Astronomical Union voted to recommend that the Hubble law be referred to as the Hubble-Lemaître law, the IAU statement explains that the change was meant to honor both men for their fundamental contributions and to acknowledge Lemaître's role in the scientific theory of the expansion of the universe. That recommendation did not settle every historical disagreement. Some scholars welcomed it as overdue. Others argued that no renaming can fully capture the collective and gradual nature of the discovery. But the vote itself is revealing. Nearly a century after the original work, astronomy was still trying to decide how the story should be told. Perhaps that is the deepest lesson of this section. Scientific discovery is not only the finding of a pattern in nature, it is also the later finding of a pattern in memory. And those two patterns do not always match. Nature may speak through many observers, many instruments, many half-understood hints, and many partial solutions. History, by contrast, often prefers a single name, a single date, a single paper that can stand for everything. The expanding universe resists that preference more stubbornly than most discoveries do. Its observational basis began with Slipher. Its mathematical opening belongs to Friedman. Its first full theoretical and empirical synthesis belongs to Lemaître. Its powerful public observational consolidation belongs to Hubble and Humassons. And around all of them move Wurtz, Lundmark, De Sitter, Eddington, and others who helped make the result thinkable. Once you see the story that way, the question of credit stops feeling like a distraction from the science. It becomes part of the science's human texture. Because what had been discovered here was not merely a relation between distance and redshift. It was a new condition of reality. The universe was no longer a stable backdrop. It had become a historical thing, a cosmos that could change with time. And that, in the end, is where the film must go next. After the arguments over names, after the missing paragraphs, after the caution and the prestige and the narrowing of memory, there remains the larger change itself, the moment human beings realize that the universe has a past, and that once it began to expand in thought, it could never quite return to stillness again. Once the struggle over names begins to fade, a larger fact remains behind it, almost untouched by the disputes that helped obscure it. However the credit is distributed, however carefully one restores Slipher, Lemaître, Humasson, Friedman, Hubble, and the others to their proper places, the underlying change is the same. A relation had been found in the sky that no older static picture could absorb without strain. Galaxies did not seem to occupy a fixed arrangement, suspended forever in cosmic stillness. Their light suggested ordered recession. Their distances suggested a large common pattern. And once that pattern was allowed to mean what it seemed to mean, the universe changed category in the human mind. It stopped being only a structure. It became a story. That transformation did not happen in one public instant. It settled slowly, unevenly, the way many deep changes in thought do. Even after the velocity-distance relation had entered astronomy, interpretation remained cautious in some quarters, reluctant in others. Hubble himself, as we have seen, did not rush toward maximal claims. The redshifts were real. The relation was real. But the full physical meaning still sat inside a field of intellectual tension. Yet the direction of travel had become increasingly difficult to resist. The old static cosmos had lost the quiet authority it once possessed. A universe that changes with time was no longer an eccentric theoretical possibility. It had become the leading way of making sense of what the telescopes were actually saying. You can feel that change vividly if you picture Einstein arriving in California in the early 1930s, moving through Pasadena and eventually up toward Mount Wilson, where the great telescope and the astronomical results it had helped produce formed part of the background to discussions already reshaping cosmology. The exact weight one assigns to any single visit should not be exaggerated. But historically, the period matters. Einstein had once modified his equations in order to preserve cosmic stillness. Now the balance of evidence, joined to the growing plausibility of dynamic solutions, was moving against that preference. By the early 1930s, he had abandoned the cosmological constant as a device for maintaining a static universe, and the Einstein de Sitter model of 1932 gave expression to a very different attitude. A universe no longer artificially held in place, but allowed to evolve. The shift was not merely technical. One of the greatest scientific minds of the age had yielded, gradually and without theatricality, to the idea that the cosmos need not sit still to be intelligible. There is a special kind of significance in that surrender. Einstein's earlier static model had been an attempt to preserve a world in equilibrium, a cosmos complete enough to endure without development. Letting go of that picture meant allowing time to enter the universe at the deepest level. Time had always existed inside the universe, of course, measured by planetary motion, stellar evolution, decay, and change. But now time reached the structure of the whole. The universe itself could age. It could once have been denser, smaller, different in form. It might continue changing long after the present arrangement of galaxies had vanished from any future sky. This is why the discovery of expansion altered more than astronomy. It changed the grammar of reality. Yet almost as soon as that broader meaning emerged, another difficulty arose from within it. If the galaxies are receding from one another, and if one traces that recession backward in thought, then the universe in the past must have been more compact. Push the idea farther, and the compression becomes extreme, even without later refinements. The implication was already unsettling. The cosmos now seemed to point not only toward change, but toward origin, and because Hubble's early value for the expansion rate was so high, the implied age of the universe came out alarmingly small, smaller, in fact, than many estimates for the age of the Earth and older stars. The universe had acquired a history, yes, but at first it seemed to have acquired one that was too short. This was the famous age problem, and it is one of the most revealing episodes in the entire history of cosmology. It shows how a discovery can be fundamentally right while still arriving with numbers that make it hard to live with. The form of the truth had become visible. The cosmos was not static, but the scale of that truth had not yet settled into coherence. If the universe was only around 2 billion years old under the early expansion estimates, then geology, stellar evolution, and cosmology appeared to be speaking incompatible languages. the Earth seemed too old for the universe that contained it. This was not a minor embarrassment. It was a deep crack running through the first modern picture of an evolving cosmos. And yet the response to that crack was not a wholesale retreat into the static universe. Instead, it became part of the long labor of calibration, interpretation, and refinement through which cosmology slowly learned how to make its expanding history numerically credible. That willingness to stay with an imperfect truth is one of the most admirable features of science at its best. Had expansion been only a fashionable idea, the age problem might have broken it. But the underlying evidence was too persistent, too widely connected, and too conceptually fertile to be dismissed. Astronomers and physicists did what serious investigators tend to do when reality offers them a pattern that is convincing in shape but troubling in detail. They kept the pattern in view while reworking the details. The distance scale would be corrected. The classification of Cepheids would be refined. The expansion rate would fall. The age of the universe would lengthen. But already, before those later repairs were complete, a more radical habit of thought had begun to take hold. People were learning to ask not whether the universe changes, but how its history should be reconstructed. That shift opened the way to an even more daring idea, one associated above all with Lemaître. In 1931, the same year his earlier 1927 paper was finally translated into English in altered form. He proposed that if the universe is expanding now, then one may imagine a far earlier state in which all the matter and energy of the cosmos existed in an extremely compact condition. He called it the primeval atom. The phrase has a slightly antique sound today, but its imaginative force was enormous. The expanding universe no longer pointed only to recession. It pointed toward a beginning, unlike anything classical astronomy had known how to discuss. The sky was no longer simply a distribution of objects extended through space. It had become the aftermath of an event. That is the moment when cosmology begins to feel genuinely modern. Once the universe has a past, astronomy is no longer only the study of what is out there. It becomes an inquiry into what has happened. The stars and galaxies become traces as much as objects. Their present arrangement ceases to be merely descriptive. It becomes evidential. To observe the heavens is, in some measure, to read consequences. This changes the emotional tone of the field. The old static universe had the dignity of permanence. The new universe had the drama of development, though not the melodramatic kind. Its grandeur lay in sequence, transformation, and irreversibility. It had once been different. It would one day be different again. There was also a philosophical cost to this new understanding, or perhaps a philosophical discipline. A static universe allows the human mind to imagine a kind of ultimate backdrop, a reality that simply is, without having to explain how it came to take on its present form. An expanding universe takes that comfort away. It invites the question of why the cosmos has the history it does, and not another. It draws attention to the contingency of the present arrangement. Galaxies are where they are, because the universe evolved into a state that permits such structures. Stars shine because matter cooled, condensed, and changed. Even the possibility of life becomes linked, however indirectly, to cosmic timing. The heavens stop being an eternal architecture and start resembling a process in which the present moment is only one phase. That change reaches farther than professional science. Imagine the ordinary act of looking at the night sky after the idea of expansion has fully entered culture. The stars are still beautiful. Constellations still seem stable on a human timescale. The Milky Way still stretches as a band of unresolved light. Outwardly, the sky has not altered at all, but inwardly, the act of seeing it has changed. You are no longer looking at a permanent ceiling. You are looking into something that has developed. The darkness above is historical. It belongs to a universe that once occupied a denser state and has been unfolding for immense spans of time. The stars are not fixed, ornaments hung in place beyond change. They are temporary participants in a larger becoming. That is one of the strangest achievements of modern thought, to preserve the ancient emotional power of the night sky, while completely transforming what that sky means. And even now, the idea remains difficult in a way that says something important about the human mind. We do not naturally think in terms of expanding space. We imagine explosions into pre-existing emptiness, or objects moving away from a center through a larger surrounding void. But the cosmological picture that emerged from relativity is subtler and less intuitive than that. Expansion does not necessarily mean galaxies flying outward from one privileged middle into a ready-made external container. It means that on large scales, the metric structure of the universe changes with time, so that the distances between galaxies participating in the general flow increase. That is not how daily life trains us to imagine motion. The expanding universe is therefore historically important, not only because it was discovered, but because it forced human intuition to stretch beyond the analogies of ordinary experience. In that sense, the discovery resembles other great revolutions in science, while also surpassing many of them in scale. Copernicus displaced the Earth from the center of the cosmos. Shapley displaced the Sun from the center of the Milky Way. Hubble and others helped dissolve the Milky Way into one galaxy among many. Expansion added another displacement, quieter, but perhaps even more profound. It displaced permanence. The universe itself was no longer exempt from development. There would be no final refuge in the idea that whatever changed within the cosmos as a whole remained serenely the same. Time had reached the whole, and with that, scientific curiosity acquired a new task. It was no longer enough to map the contents of the universe. One now had to reconstruct its past, infer its earlier conditions, and ask what present observations could reveal about states of reality no human being could ever witness directly. Cosmology became, in a very real sense, a historical science. The astronomer, like the geologist or paleontologist, had to learn how to read surviving traces and work backward from them. Redshifts, galaxy distributions, stellar populations, chemical abundances, later the microwave background. All these would become pieces of a cosmic archive. The expanding universe made that mode of inquiry possible. It taught science to treat the cosmos as something from which earlier chapters could be recovered. There is a quiet grandeur in that change of method. Human beings are small and brief, limited to a narrow temperature range on one planet around one star. Yet by attending carefully to faint light, by refining instruments, by correcting errors, by arguing honestly about models, and by staying with questions longer than comfort would prefer, they managed to discover that the universe has a biography. They found that reality on the largest scale is not an inert arrangement, but an unfolding one. The discovery did not give them mastery over the cosmos. It gave them something more subtle, participation in its intelligibility. That is why the expanding universe still feels strange today, even to people who learned the phrase in school and have repeated it for years without surprise. If one pauses and lets the words recover their force, They remain almost unsettling. The universe is expanding. The galaxies are not merely arranged, they are receding within a changing cosmic order. Space and time are not a silent frame surrounding events. They belong to the event. And behind the present sky, there lies a past so different from the visible world now overhead that ordinary imagination, left to itself, would never have invented it. The fact that such a thing could be known at all is one of the triumphs of human thought. What remains, then, is not a return to stillness, but a different kind of calm. The calm that comes from understanding that knowledge does not end by making the universe familiar. Sometimes it deepens the mystery while clarifying its form. The expanding universe did exactly that. It took the oldest object of contemplation, the night sky, and revealed that even it is not outside time. And once that realization enters the mind, the search for knowledge begins to feel a little different as well. Less like the possession of fixed truths, perhaps, and more like learning how to follow reality as it continues to unfold. What began as a puzzle about faint nebulae and shifting spectral lines became something much larger than an astronomical result. To discover that the universe is expanding was to discover that the cosmos has a history. It was no longer enough to imagine the heavens as a silent, permanent arrangement hanging beyond human life. The universe itself had entered time. It could change, evolve, and carry traces of a past that had once seemed beyond inquiry. In that realization, astronomy became something more than the study of distant objects. It became a way of asking how reality itself unfolds. There is something deeply moving in the path that led to that understanding. The truth did not arrive all at once, and it did not belong neatly to one person. It emerged through fragile measurements, disputed interpretations, mathematical courage, technical skill, and the persistence of people willing to remain with uncertainty longer than comfort would allow. Some saw farther because they built better instruments. Some saw farther because they trusted equations that others hesitated to follow. Some provided the crucial clue and were only later recognized for it. Together, they changed the scale of human thought. Perhaps that is one of the quiet lessons this story leaves behind. Scientific discovery is not only a matter of finding answers, it is also a discipline of learning how to live inside questions, how to notice when the world is larger than the ideas brought to meet it, and how to keep listening when nature speaks in ways that first sound impossible. The expanding universe remains one of humanity's great acts of understanding, but it also points beyond itself. Even now, the sky is not finished with us, and our search to understand it is still, in its own way, expanding.